Hello and welcome everybody to today's lecture on inverse problems in medical imaging. Before we start with the lecture today, we probably should discuss the outline of today's lecture. We will continue with solving linear inverse problems, and we will finally solve the quadratic inverse problem using eigenvalues and eigenvectors. And then after we finish with that, we will continue with linear inverse problems, but with non-quadratic ones. And there we find the singular value decomposition that helps us solving this inverse problem. Before we start, we should recap shortly with what we ended last lecture. There we had the decomposition theorem for square matrices. So let's recap that shortly. We said that a square m by m matrix A can be written as A equal to S times lambda times R transposed. And therein, S is an m by m matrix whose columns are the eigenvectors of A. R is an m by m matrix as well, and the columns of R are the eigenvectors of A transposed. And finally, lambda is the diagonal matrix where the diagonal entries are the eigenvalues that are shared by R, A, and A transposed, and the off-diagonal entries are 0. So please remember, we said when we have a matrix A and a corresponding transposed matrix, then they have the same eigenvalues, but different eigenvectors. Now, the aim is to find the inverse of this matrix A if it exists. So, first task for today is finding the inverse of a square matrix. What is actually an inverse? Let's recap that shortly. The aim is an inverse matrix so that A times A inverse is equal to A inverse times A is equal to the identity matrix. Let's recap very shortly the eigenvalue problem. So we know ASI equals lambda I SI with eigenvalue lambda I and eigenvector SI. And for now, we just assume that the inverse exists. Now we multiply the eigenvalue problem we have written down here with this matrix A inverse. So we end up on the left-hand side, A inverse ASI is equal to A inverse lambda I SI. Now remember that the matrix vector multiplication is a linear operator, so therefore this is equal to lambda I times A inverse SI. So we said we assumed that the inverse matrix exists. Hence this thing here is equal to the identity matrix. Now with that and some rearranging of the stuff, we end up in A inverse times SI is equal to 1 divided by lambda I SI. And of course only if lambda I is not 0. Here, we have actually written down the statement of the eigenvalue problem for the matrix A inverse. So what we see here immediately is that the matrix A and its inverse have the same eigenvectors. And furthermore, we can note a statement about the eigenvalues. So the eigenvalues of I inverse are given as the reciprocals of the eigenvalues of the original matrix A. Now we have a square matrix, I inverse, and we can use the decomposition theory to decompose the matrix A inverse. So we end up in A inverse being equal to S, lambda inverse R transposed, whereby we know already S and R, they are defined as in the theorem before. The only thing left is lambda. So lambda inverse is given as the diagonal matrix. With 1 divided by lambda 1, and so on up to 1 divided by lambda m. We have one problem. If lambda I is equal to 0, then 1 divided by lambda I is undefined, and hence the inverse matrix does not exist. So if all the eigenvalues are non-zero, we are out of trouble. We can build the inverse matrix. If only one eigenvalue is 0, then we're in big trouble. We cannot build the inverse matrix anymore. Now, the obvious question is, what do we gonna do when we have 0 eigenvalues? And the answer is we still try to find a solution, but we might not be so successful anymore. So we consider again the eigenvalue problem. And we assume that some of the eigenvalues are 0. What we can say is that the inverse does not exist. But we said that we still want to handle this case properly. So what we do next is we suppose that we have a certain amount of 0 and non-zero eigenvalues. So here we suppose we have P non-zero, and then n minus P, so the remaining eigenvalues are 0. We do some reordering so that we keep an overview about things. And we say that lambda 1, or the absolute value of lambda 1, should be the greatest, followed by lambda 2, and so on, with lambda p being the last, that is greater than 0. And then all the others, so lambda p plus 1 up to lambda m, should be 0. What follows is that lambda, the diagonal matrix, has now lambda 1 and lambda p on the first entries of the diagonal, followed by 0. And from the 0, we have n minus p pieces. We think about the decomposition theorem once again. And remember, it said we can write A as S times lambda times R transposed. Let's do that now. And plug the vectors and so the eigenvectors and the eigenvalues into. So we have for S, first the vector S1 up to SP. Then we have SP plus 1 up to SM. Next, we have the diagonal matrix lambda, where we have, by definition, lambda 1 to lambda p, followed by the zeros. And last, we have the matrix R. So in the first row, we have R1 going to RP, followed by RP plus 1, going to RM. Now, we multiply the first two matrices together. So we have lambda 1 S1, and so on, up to lambda P SP. And then for the last M minus P columns, we just have 0, because we multiplied the vector with 0. And then the R unchanged. So we have here M minus P rows that will be multiplied by 0. Because if you look closely, you see that here's M minus P columns that will directly influence those M minus P rows of R's. So to conclude, SP plus 1 up to SM, as well as RP plus 1 up to RM, are not needed to form the matrix A. And before we continue, we will make a few definitions with that. First, we decompose the matrix S. Remember, the matrix S contains the eigenvectors corresponding to the matrix A. We define S as being SP in the first part and S0 in the second. And SP contains the P eigenvectors associated with the non-zero eigenvalues, and S0 is everything else. Number 2, we do the same thing with R. And remember, R was the matrix containing the eigenvectors corresponding to the matrix A transposed. And last, We do the same thing for the diagonal matrix lambda. So we say lambda is decomposed into lambda p, and then we have 0 blocks everywhere else. And lambda p is just the diagonal matrix containing lambda 1 up to lambda p. And with that, we can decompose the matrix A, sorry about that, into SP times lambda p times RP transposed. So it's really nothing else than the original decomposition theorem we had. However, we got rid of all the rows and columns within the matrices S, lambda, and R that did not influence the matrix A. So regarding dimension of this stuff here, A is an m by m matrix, SP is m by p, lambda is p by p, and finally RP is p by m. So we know now what we can do when we have 0 eigenvalues. We should discuss a few things regarding this matter. First of all, if we really have 0 eigenvalues, the inverse matrix does not exist. Because we saw already that we just cannot build it, because the eigenvalues of the original matrix and the inverse matrix are connected by being the reciprocals of them. If there is a solution to the inverse problem, which might be possible even though the inverse matrix does not exist, then there are infinitely many. And we can see that using the following. We know the eigenvalue problem, and then if one of the lambda i's is 0, correspondingly lambda I times Si is 0 for all I from p plus 1 to m, where we did the ordering correspondingly. Now, if x solves the inverse problem ax equal to b, then a times x plus s1, and a is a linear operator, is the same as b plus lambda I si, which is therefore b. So we can write down a general solution in this case, and we can define it as x, so the one that solves the inverse problem, plus the sum from p plus 1 to n. Sorry, this should be m. With the definition we did, this needs to be an m. I'm sorry about that. But when you sum up here are the eigenvectors with an arbitrary weighting factor, because as soon as we have an eigenvector involved, we end up in 0. So take-home message for this topic: we can build a solution. It might not be the solution, but just an approximate of it. And if we have one, then we have arbitrary many solutions to the inverse problem. Now, we discussed quadratic inverse problem. The question quadratic but linear. The question is, what about non-quadratic but linear inverse problems? And this is what we're gonna do next. And for that, we introduce the singular value decomposition. So we discussed the general inverse problem, Gm equal to D, where now G is an n by m matrix. So we can only go back to the eigenvalue problem if n is equal to m. And if you remember, in the first lecture, we had this concept of parallel between eigenvectors and eigenvalues. And this thing here breaks down because now we have an m-dimensional vector pointing to an n-dimensional vector using the map G. So no parallel anymore. But now we should discuss what actually the idea is here. Because remember, our aim is to solve the inverse problem, where now a non-square matrix is used for it. The idea is that we just construct a square matrix where we can apply the eigenvalue problem. And once we have this eigenvalue problem ready for the new square matrix, this thing will be called singular value decomposition. So I will tell you already what the end result of the singular value decomposition is, because then we just know where we're gonna go. So the end result will look as the following. T, so the matrix we want to invert, being equal to UP times lambda P times VP transposed. We should discuss dimensions of those matrices inside. T is, as I said, an M by M matrix. Now you remember already P was before the number of non-zero eigenvalues. It will be something similar here. U will have dimension N by P. Lambda will have dimension P by P. And finally, VP transpose will have dimension P by M. So now the question left is, what are those matrices U, lambda, and P doing? So UP are the P n-dimensional eigenvectors of the matrix T transposed. So T, the original one, was non-square, therefore we couldn't do anything with eigenvalues and eigenvectors. But actually T transposed is squared, so we can define the eigenvalues and eigenvectors of it. Now VP are again P. And they're the m-dimensional eigenvectors of T transposed times T. And finally, lambda P is again a diagonal matrix. Containing P so-called singular values. And you will see in a couple of minutes what those singular values are. So let us start. First, we need a new matrix where we can actually apply the eigenvalue problem. So we define B as 0, T transposed, and 0 again. So B is a block matrix. We should discuss the dimension of B shortly. B itself is n plus m by n plus m. Then we have given the dimension of T, and therefore we have n here, m here, and correspondingly size n here and m here. There's something you should note. If we build by transposed, then we end up with B itself. And the mathematical definition or wording for this is Hermitian. And what we then have is, on the one hand, real eigenvalues, and orthogonal eigenvectors. Now, let us define the original inverse problem regarding G. And let's call this problem here star. Now, analogously, we define an inverse problem regarding T transposed. So we say T transposed times Y should be equal to C. And we call this problem here star star. So we now combine those two. Using our newly formed matrix B, and we end up in 0, T transposed T 0 times Y M being equal to D and C. Or written down shortly, B times Z is equal to some B. Regarding dimensions, we said B is M plus M by N plus M. Z is N plus M by 1, and B is N plus M by 1. So we have found an inverse problem using a square matrix. Now we can apply the eigenvalue problem to this square matrix, where we originally wanted to solve an inverse problem using a non-square matrix. What we do next is we discuss the eigenvalue problem for the square matrix B, which we can. So let's write it down. We have B times omega I is eta I omega I, for I being equal to 1 up to n plus m. So we say that the omega i's are the eigenvectors and the eta i's are the corresponding eigenvalues. We know that the eta I are real. Just showed it on the previous slide. And now we arrange the eigenvectors of B a bit. We say that omega should contain omega 1 up to omega n plus n. And please note, also from the previous slide, that since the eigenvectors are orthogonal, that omega t times omega is the same as omega transposed is the identity matrix. So next, please remember, B is a block matrix consisting of 4 blocks in total. So we try to partition the eigenvectors of B a bit. So we consider let's say we have ui first and then some vi second. And regarding the size of the ui is n, and of the vi is n. Sorry. Now, the eigenvalue problem for B can be written as 0, T transposed 0 and T. Then we have the ui and the vi times eta I ui vi. I from 1 to n plus m. Now, last thing we're doing here. This is nothing else than T times vi I did a mistake here, I'm sorry. It should be t here and 0 here. So we have t times vi is equal to eta I ui, and from 1 to n plus m. And on the other hand, we have t transpose ui is equal to eta I vi e again from 1 to m. And we call this thing here shifted eigenvalue problem for t. Next obvious thing, we would like to solve this shifted eigenvalue problem. So we start with the following procedure. And just to have it in mind, let us write down here what shifted eigenvalue problem was. So we had t vi equals eta I ui, and t transpose ui equals eta I vi. Get back to the procedure. We start with the second of those two equations. And we multiply eta I. And since t transposed is a linear operator, we can write t transposed eta I ui equals eta I squared vi. Now, on the other hand, we know that t vi equals eta I ui. So we can plug the following thing here in. And we end up in t transposed t vi equals eta I squared vi for I from 1 to m. So we have an eigenvalue problem here. Let's discuss a few things. First of all, T transpose T is a Hamilton matrix. So the eta I squared are real. And therefore, they're not only real, but they're greater or equal than 0. And T transpose T is positive, semi-definite. We can define a matrix notation once again. It says that T transposed T V equals V times M, whereby V contains the eigenvectors and M contains the eigenvalues. And last, the matrix V is orthogonal. So V transposed equals V transposed V equals the identity. So we just discussed one of those two equations. It is time now for the other one. Again, we start with TVI being equal to eta I ui, and we multiply again eta I. So T eta I vi equals eta I squared ui We know that T transpose ui equals eta I vi. So we have the same thing going on here and here. And therefore, we end up in T transpose ui equal to eta I squared ui for I from 1 to n, which is the second eigenvalue problem. We could discuss a few things about this again. T transpose is Hermitian. Like before, T transpose is positive semi-definite. And like before, we define a matrix notation once again. So we end up in T transpose u equal to u times n, whereby u contains the vectors u1 to un, and n is the diagonal matrix with the eta i's. Last, u is orthogonal, meaning u transpose u is equal to u transposed, which is the identity. So we're back with two eigenvalue problems, which we can solve. The eigenvalue, using eigenvalues and eigenvectors, as we've seen already half an hour ago, we can invert square matrices. Now, obviously, we would like to do the same or use the same for the non-square matrices. Before doing so, we define singular values. So lambda I is defined as the positive square root of eta I squared. So it is the positive square root of the eigenvalues of T transposed T or T transposed. Please note, lambda I is not an eigenvalue of T or T transposed. And lambda I is called singular value. Now, once again, we define a matrix corresponding to the lambda i's. And we have here two cases. Case 1, m greater than n. Here, lambda is given as lambda 1 to lambda n, and 0 here. Thereby, we have lambda being an n by m matrix. Here we have n, m minus n, and n. Case 2, n greater than m. Here we have lambda equal to lambda 1 lambda now is an n by m matrix. Here we have m, n minus m, and m. Now we can define, or we can write down the shifted eigenvalue problem in matrix notation. And we have on the one hand Tv equals U lambda, and on the other hand T transposed U equals V lambda transposed. Last thing for today, we would like to derive something like a fundamental decomposition theory for the non-square matrix T. Let us shortly recall what we did in the squares case. We had A being equal to S times lambda times R transposed using eigenvalues and eigenvectors. Now, the question is, what are we going to do with a general matrix T? So we start with the shifted eigenvalue problem in matrix notation. So TV is U times lambda. And we multiply now V transposed from the right-hand side. So T, V transposed is U lambda V transposed. Now remember, we said that the matrix V is orthogonal, and therefore we have here the identity matrix. So we end up in T being equal to U times lambda times V transposed. Or analogously, we could do the same thing starting with the other shifted eigenvalue problem. And we get T transposed is V lambda transposed U transposed. Now, there's one thing left. We did not discuss what to do if some of the singular values are 0. Like before, like in the squares case, then they do not have a valuable input for building T and T transposed. So basically, we could just get rid of them. So like in the squares case, we start with rearranging the lambda i's. And we say that the first one should have the greatest absolute value, followed by the second up to p, and then lambda p plus 1 up to lambda n should have size 0. So accordingly, we define u as up, u0, v as vp, v0, and lambda as lambda p and 0. We end with T being equal to up lambda p vp transpose. Same argument we used before. And we call this thing the singular value decomposition for T. So the question left is, what are the dimensions of the matrices? T is n by m, up is n by p, lambda p is p by p, and finally Vp is p by m. This is basically it. Now we can make a few notes. Please note that we started with an arbitrary matrix n by m. It is non-square. The eigenvector matrix UP contains the p n-dimensional eigenvectors of this corresponding problem that are associated with the non-zero singular values lambda I. Same thing for Vp. So Vp contains the p m-dimensional eigenvectors of the second eigenvalue problem associated with the non-zero singular values. And finally, the singular value matrix lambda contains the p non-zero singular values lambda I. So that's it for today. Next time on Wednesday, we will discuss actually how to perform the singular value decomposition. And we will stick a bit further to the non-square but linear inverse problems, and we find a few additional solution methods of solving them. Thank you.